Okay, so another typical question. The following procedure was carried out at 298 Kelvin to determine the distribution coefficient of Kd. So, okay, it's a monobasic organic acid between dichloromethane and water. Okay, so the idea is clear. So you have two solution you need to find. So 50 cubic centimeter of aqueous acid. So here you use 50 cubic centimeter, and let's say the aqueous acid is X. Normally we take HA, but okay, let's say this is as X for an example. Okay, X is equal to HA. And the concentration is given 0.2 m. This is cubic centimeter. Centimeter. So cubic centimeter of aqueous solution were mixed vigorously with 10. So this is dichloromethane, let's say. So this is 10 cubic centimeter of the. I would put here the organic phase, and this is the aqueous phase. Sorry. And the two layers were allowed to separate. Okay. Thereafter, dichloromethane layer in the bottom. Okay. So they say this is in the bottom. So anyway, of the flask drain out, and 10 cubic centimeter of NaOH solution were required to neutralize the acid remaining in the aqueous layer. So basically what they say is, so they remove this part, okay, and they titrate this part. Titrate this part using NaOH. So basically here this is an acid HA. So there will be a 1:1 stoichiometry between HA and NaOH. So we can calculate the moles of NaOH as 10 into 10 to the power minus 3 is the volume times the concentration is 0.02. So this gives 0.2 into 10 to the power minus 3 means 2 into 10 to the power minus 4 moles of NaOH will be consumed. Here, for the acid remaining in the aqueous layer. Okay. So here you shake it and you allow the layers to separate, and you remove this dichloromethane layer. So there will be some amount of HA in the dichloromethane layer, and here some amount will be there. So what they do is they remove the dichloromethane and they titrate this aqueous layer, and they find it needs this amount of NaOH. So here we know NaOH is to this HA reaction is 1:1. So the amount of HA that would be remaining in his aqueous layer is also this one. Okay. So this X concentration in this aqueous layer would be 2 into 10 to the power minus 4 moles divided by the volume 50 into 10 to the power minus 3 decimeter. Then they have given, assume that the acid does not dimerize in the organic phase. So normally some acids like carboxylic acid dimerize. We need to find the Kd of the acid between dichloromethane and water. So you need to find Kd equal X concentration in organic over X concentration in aqueous. So we know already the X concentration in aqueous. So I will cut this one to this one. There will be -1 here. So this would be like 0.2 divided by 50. Okay. And we need to find the X concentration in organic phase. So this would be straightforward, because we know the initial amount of X, right, in the aqueous phase. So the initial amount will be 0.2, 50 times 10 to the power minus 3. So basically here 50 times 2 is 10, 10 into 10 to the power minus 3. So I would take this as 100 into 10 to the power minus 4, because I have taken here also 10 to the power minus 4. So its concentration, so this is the initial amount that we have used for this particular shaking, and you know the amount that is remaining in the aqueous phase. So based on that, you can calculate amount that is present in the organic phase would be, so N organic would be N initial minus N remaining, right? N remaining in the aqueous phase. So basically 100 minus 2. So it would be 98 into 10 to the power minus 4 moles, right? And to find the concentration, you need to divide by the volume. Now remember, here the volume is 50 cubic centimeter, but here the volume is only 10 cubic centimeter. So don't confuse with that. So here it will be 10 into 10 to the power minus 3 decimeter. So you again you can cut this to this one minus 1. So it will be 9.8 divided by 10, right? So you can cut this to this one. So you do the calculation, then you will get this 245. Right. So this is the normal way of doing this calculation. The important thing that you need to understand here is that the initial amount is given because you have this HA acid in the aqueous form. Because it dissolves in a water solution, because it can protect, right? But here they say even you should not consider. They don't say, but you need to understand that you should not consider about the dissociation of HA in the aqueous phase as well. Because if you consider about the dissociation of HA in the aqueous phase, you need to separately calculate the amount of HA that is not dissociated into H plus and A minus. But they have not given in that sort of a way. You just need to think it is not dissociated, okay, and calculate. So what we did, we initially calculate the initial amount. So this is 100 into 10 to the power minus 4 moles. Then we calculate the amount in the aqueous phase, remaining amounts. This was 2 into 10 to the power minus 4 moles, if I am correct. Yeah. And then we get the remaining, remaining means the amount actually that is went to the organic phase by subtracting the initial amount and the remaining in the aqueous. So it is 100 into 10 to the power minus 4 minus 2 into 10 to the power minus 4. So which is 98 into 10 to the power minus 4. Then we divide by the volume to get the concentration in each phase. Don't forget, here the volume is 50, here the volume is 10. Then you plug for KD and 5. That's it. Okay.